We have a curated list of 10 speakers from diverse research backgrounds, which will also give us an idea of what the topical research areas are that are being carried out across the country. So first of all, we'll have Vivek from IT Madras. So his topic is PN-based guidance strategies for containing a non-maneuvering target using multiple pursuers. Over to you, Vivek.
Thank you. As we all know, nowadays the drone has been a buzzword because of the war situation happening. But there is another catch to this. In some days, given the technological advancements, we will be seeing drones above our head at any point of the time in everyday life. So during that time, even a seemingly harmless drone which violates the airspace requirements will be a potential safety threat. During to tackle such thing, we cannot use the conventional methods like the shoot to kill, because that would create debris problem, which could be more harm than the actual threat. In a most popular populated areas, in populated civilian areas, this will be a bigger damage. So one viable alternative is to send a team of UAVs to contain the threat UAV and safely guide it away or capture it using the net. So but that is also not an easy task, that comes with its own challenges. First, the individual UAV have to approach the target UAV from a desired direction, at any desired direction. Then all the group of UAVs should reach the target UAV simultaneously. That will be a successful containment. Then in some application, we may have to move the UAV in a formation controlled fashion, where we are carrying a net kind of things to capture it. So there should be a formation controlled movement towards the target UAV. So for to address these challenges, in my PhD thesis, I proposed PN-based guidance strategies due to its obvious advantages. So for developing the PN-based guidance strategies, we rely on the angular plane as shown in the first figure, where the x-axis is the LOS angle and the y-axis is the heading angle. Using this plane gives an advantage that the PN trajectories are just a straight line. Due to the linear relationship between the LOS and the heading, the PN trajectories will be just straight line with the slope as the navigation gain. And it is also easy to prove all the existing result in the literature by just using the geometrical arguments in this plane. So now to achieve any desired collision configuration, which is shown as the green line, any a particular configuration is just a point on the green line. To reach the green line, we have to just find the suitable pieces of straight line, that by changing the gain we can create a suitable subfaces of different guidance spaces to reach the required configuration. So once we have achieved every desired possible points which corresponds to the desired terminal angles, now we can use this framework to build upon the other time requirements that is required for the containment. So the next work was to encircle a stationary target, we have to simultaneously arrive at the stationary target. So we can add an extra phase that will adjust the time to go over the given first angle constraint case. Now just by adjusting the navigation gain, it is not sufficient for a moving target case. So we adjusted the speeds for which the analytical guarantees can be given from the understanding of the phase plane, angular phase plane. Finally, a two pursuer formation controlled guidance strategy was proposed, which could follow the individual trajectories. The two pursuers can follow the individual trajectories that were earlier given by the earlier developed guidance strategies. In summary, the guidance strategies proposed as a part of my PhD thesis can be a building block for developing efficient CUAV counter UAV system, particularly in a civilian airspace. And the trajectory shaping in the phase plane, angular phase plane, can easily facilitate the design of the guidance strategies. The future research scope in this direction are to extend this guidance strategy towards the holistic 3D scenarios and towards and against maneuvering targets. Thank you.
Quick questions for, we have just half a second. Any question? Sorry, half a minute. Okay, okay, then we'll move on to the next, Ishfaq. So the next talk in this session is by Ishfaq Zahur Bhatt, and he will be talking on optimal tracking and visibility analysis of a target spacecraft using multiple chaser in the cislunar space. So Ishfaq is from IC Bangalore, and over to you, Ishfaq.
Good afternoon, everyone. Thanks, Suryadi, for introduction. So, cislunar space is the three-dimensional space beyond geosynchronous orbit, but still under the gravitational influence of Earth and Moon. L1 to L5 shows the Lagrange points in this space, and this shows the scale of the distance in this region. So, it provides opportunities for future human exploration of deep space. With the increasing importance in the planned space missions, it becomes important to track objectives in cislunar space. But a single observer cannot do it, and we cannot use the moon-based observers due to its fast dynamics. So cislunar space dynamics is modeled with the three-body problem, and here are the periodic three-body motions for spatialized initial conditions, and this is for the deviated initial condition. And if we assume one of the masses to be smaller as compared to the other two, and take the rotating frame, we get what is known as circular restricted three-body problem, and this is the nonlinear dynamics which we get. And this shows the trajectory in the inertial and the rotating frame for a spacecraft. So if we linearize this nonlinear dynamic model about the Lagrange point and use the differential correction method, we will get the periodic orbits, for example, halo orbit, and with the variation of some parameter, we can get a planar family known as Lyapunov family, from which axial and halo families bifurcate. So coming to the problem statement, we take the target and the multiple chasers on the two different halo orbits with the restrictions on the sensor range. The objective here is to maximize the tracking time, and we also include the visibility restraints as a occlusion cones from Sun, Earth, and Moon. So we formulated it as the maximization problem with decision variables as the initial condition of chaser and the target. As a solution methodology, we discretized the trajectories of target and the chaser, and this shows the results for single and the multiple chasers, and this shows the optimal trajectories for the chaser. So coming to the visibility part, the position of the Sun was chosen from bicircular restricted four-body problem, and we use the Cannon base model for evaluating the visibility as a apparent magnitude given by this equation. So these shows the visibility of observer moving in the halo orbits within this collision cones for different orbits, halo as well as the axial. And the red one shows the time periods where it is not visible, and this shows all the variation of this apparent magnitude with respect to the time. Thank you. These are the references on the basis of which I made this presentation, and these are some other references. Thank you.
We have 2 minutes for questions now. Yeah. Go.
In the linearized dynamics, you said that you get two trajectories which bifurcate from a certain point. So that dynamics part, like what is that bifurcation parameter which changes to, give rise to these two kinds of trajectories here?
Okay, so basically the what I was saying is, okay, let me go. Yeah.
Yeah, in this.
So if we take if we take this as the parameter, the distance from this Lagrange point or the origin which we have taken, if we vary this, we will get different these kind of orbits which is planar. But then if we move out of this plane from particular amplitude, we will get this family, and from the other amplitude, larger amplitudes, we will get this another three-dimensional family, which is known as the Halo family.
Okay. So
basically
distance
it is
from
the
the
Z
left.
parameter.
Okay, yeah, got it. Yeah.
One quick question.
Thank you.
Thank you, Ishfaq. Next up, we have Shubham. Shubham is a PhD student at IIT Madras, and he will be talking on general reference path following guidance in 3D. Over to you, Shubham.
Thank you. Yeah. So hello everyone. So we know for any kind of autonomous vehicle application to go from like point A to point B, it is expected from the UAV to follow any dedicated path as precisely as possible, such as like applications such as surveillance, search and rescue, drone delivery, etc. So which necessitates the requirement of any path following algorithm. So where the key requirement from the algorithm should be like it should be able to follow any kind of general reference path, and where the without compromising the tracking performance, and the generated algorithm should be model dependent. It should not be dependent on the specific models, and generated command should be in realistic threshold. So for that here we are presenting a vector field based path following method which we are working on currently. And so let's consider here like one desired path given in the figure 1, and at some point I am at P position. So like to define a vector field based on my current position and like my closest point P ref, I can, let's say, like I will define one plane, let's say pi, as shown in the figure 2. So and at P reference point, if I define one like tangent vector as shown in the figure 1, and using these two basis vector, that is like joining the line P and P ref and the TP, if we can define one if we use these two basis vector, we can define the pi plane, and if we define one vector field on this pi plane, we can instantaneously create one desired vector direction, and which will eventually guide me towards the path, and able to follow the path as what is the requirement. So like for that we defined our vector field as defined in equation 1, and the theta is defined in equation 2. So this Vd will ensure that when you are away from the path, that is like d will be the magnitude of d is high, cross check error is high. So the vector field will guide me towards the path, and when I am almost closer to the path or almost aligned with the path, like I will follow the TP vector, which is the tangent vector of the path. So to follow this desired vector field, this is the acceleration command is given in equation 3, where k is the magnitude of the acceleration command. So using this and some nonlinear control existing result if we use, and we can show that our instantaneous velocity vector will be able to align with the desired vector field in some finite time, and our desired cross check error will go to 0 asymptotically. So this acceleration command, as you can see, it will ensure that it only change the direction, not the velocity, so not the magnitude of the velocity. So as a result, we will be able to use it for 3D application, and also like it doesn't require to define the vector field, doesn't require any parametric representation of the path. So like we will be able to represent any complex generic path. Yeah, and this is the simulation. So I showed one sample case simulation here. So thank you.
Questions? Okay.
are so many path following algorithms already there.
Yes, sir.
Why this?
Why is this? So in existing literature, most of them are like maintaining like planar movement, most of them, and like whatever existing 3D path following theirs are like they are having they require like some kind of representation of the path, like it should be like circular, or like I can represent with with respect to some parametric representation or something like that. So instead of that, here we don't need that kind of thing. So if we know only the waypoint, like for any kind of complex path, we can define the vector field, and like we can tune our vector field as based on our requirement, and which will ensure that we will able to follow any kind of path as like if it is smooth enough.
Okay. Thank you, Shubham.
Thank you.
So the next talk we have is by Sai Abhinay, who is also from IC Bangalore, and he will be talking on collaborative aerial slung load transportation and manipulation. Over to you, Abhinay.
Thanks, Surya. So, as you can see, there are 4 keywords in the title. That is collaborative, slung load, transportation, and manipulation. So we are defining 2 problems here. So in both of them, the common thing is the payload is attached using cables to multiple UAVs. So in the first problem of transportation, we are only considering the position control of the payload. We are not worried about the orientation of the payload. Whereas in manipulation, we want to control both the position and orientation of the payload. So the applications are, for the transportation case, consider transporting payloads of irregular shapes and sizes to remote locations. So that is one. In the manipulation case, one use case would be wherein you need inspection of the infrastructure, something like electrical line. So we can attach a manipulator to the platform at the end, where we can maintain constant orientation of the platform, and we can use the manipulator for inspection or some intervention that is needed. So there are predominantly 2 research tools that we are using in this work. So one is Koopman operator theory and optimal control. So first I'll explain Koopman operator theory and why is that we are choosing this. So Koopman operator theory basically is used to represent the nonlinear dynamics using a global linear model, but the catch here is it's an infinite dimensional model. So the game here is to compute a finite dimensional approximation which effectively captures the nonlinear dynamics, and once the linear model is obtained, then we'll be using a model predictive control like framework, wherein we'll use the obtained model. So here we can see that so this is the manifold on which the state space is, the nonlinear dynamics are evolving. So using Koopman theory, we'll project it into a higher dimensional state space. So these are called observables. So the Koopman operator actually acts on the observables, which are nothing but functions of the state space. So the question we're trying to answer here is the obtained linear model using Koopman operator theory, will it enable us in solving optimal control problems in real time on resource constraint and on onboard computers? So the criteria that we'll be using to analyze the results are model fidelity and optimality of the solution. So there's one preliminary work that we have done. So we have designed a model predictive controller for a single UAV carrying a slung load, and we have used a technique called dynamic mode decomposition with control. So it basically gives a linear approximation using the data collected from. So we have simulated the nonlinear model to collect the data, and also have considered the effect of external disturbances, and we were able to show that it results in a satisfactory performance of trajectory tracking. But we'll be looking at what other inherent properties of the dynamics can be used to exploit, can we exploit in getting a good fidelity linear model. Thank you.
Questions for Abhinay?
Yeah, so it's not the linear model that we obtain, it's not very good. I mean, if we compare it with a Taylor series approximation model that we get, this I don't think will offer advantages. So we'll have to look at, so in dynamic mode decomposition, we are not making a choice of basis. So the higher dimensional space in which we want to project, that is not made here. So there are techniques which we can use. So as I said, the game here is to choose a proper set of bases which will capture the nonlinear dynamics in the area we want to operate.
What are the bases that you? Do I have to? What are the bases that you are choosing?
In dynamic mode decomposition, there is no basis. It's just a state vector. Yeah.
Just it's a general question that you use MPC. Why not others controller like sliding mode and PID? Is there any reason behind it?
No, the main reason is to incorporate constraints on control and state. So that's the only reason we are doing MPC. Otherwise, we can use any other model-based control.
Okay, thanks.
I have an application-oriented question. So in the second slide, you discussed about manipulating the rigid body and orienting it into a different, let's say, not planar or maybe let's say oblique kind of formation, and then transport it. Is that the objective as well? Like through the collaborative operation of the multi-rotor vehicles, you can actually orient those payloads in such a way that you can.
Yeah.
Okay. Yeah. That's.
Yeah.
Yeah. That's just query.
Yeah.
Thanks.
Thank you.
Thanks, Abhinay, for the talk. Next up, we have Vinita. So Vinita is a PhD student at IISER Bhopal, and she will be talking on event-driven CBBA with reduced communications. Over to you.
Thank you. Hello, everyone. So today I'm going to talk on event-driven CBBA with reduced communication. So this is an task allocation approach. So here, for the motivation, like multi-UAV systems are very useful in real-world applications, like you can see in search and rescue, agriculture, planetary exploration, and in defense as well. So here, they are like heterogeneity capability, and the cooperation can be used for tasks which demands different agents. So here in this multi-UAV systems, the multi-robot task allocation, which can also be known as multi-UAV task allocation, is a very well explored area. So here, when we talk about the multi-robot task allocation, the communication plays a crucial role. So whether we talk about the centralized approach or decentralized approach, everywhere the communication is very crucial. So whether we want to like share the assignment for each agent, or the agents are sharing their situational awareness. So here, if we take the communication as a graph, so here you can see the two agents are communicating. So when there are less agent, it is with limited bandwidth, the communication is okay. But when we scale it for like large number of agents, so here if we take for 5 agents, you can see in the for the agent in the middle, if there are multiple agents sharing at the same point, at same channel, so this can cause the network congestions, and which will result in the collision of the packet. Eventually, it will result in packet drops. So I'm going to consider the communication aspect of the multi-robot task allocation. Here we chose the consensus-based bundle algorithm. Here it is an iterative process, and it is a market-based decentralized approach. It iterates over auction phase and the consensus phase. Here the agents bid on the bundle of the task, they make their list and then communicate with their neighbors. And after communicating, they like converge on a conflict-free assignment. So it iterates until it get the convergence. So they have also given the convergence bound and also the lower bound for the performance. So here in the CBBA consensus phase, in every iteration, every agent broadcasts their information. So for the 1,000 agents, it is very congested. So we we propose the event-driven CBBA, where in the consensus, every agent will broadcast only if the event has happened. Otherwise, it will only receive the information. So by implementing this, we get very good results. So here you can see this is for this is for the 5 to 50 agents we took, and this is here. This is the number of iteration it take to converge, and here you can see the red line, the flat line is for CBBA, where every agent took same amount of broadcast in every iteration, but in CBBA after few iteration it decreases. So here we ran the Monte Carlo simulation for varying the number of bundle length, and we achieve this is the percentage reduction in the broadcast, and this is the solution. So without compromising on the solution part, we get the good results in the communication, and so we achieve up to 52% reduction in the communication, and also we proved by theorem we proved that EDCBPA preserves the theoretical guarantees. And for the future work, for the scenario here, here the communication was ideal, but for future we are taking the real world like bit error rate and packet error rate, how it will perform when we consider the ad hoc Wi-Fi network, and also we'll planning to do the hardware experiment. Yeah, thank you.
Questions?
I have a question.
Okay.
How are you detecting the event? Like what sort of event?
So here the agent shares some local situational awareness. So when in the iteration agent has already shared the information, then we are preventing them to share. If it has something new to share, then only it will share.
Okay. So the information is prior to it.
Sorry?
Information is known prior to it.
Yeah.
Okay.
Thanks.
Any more questions? Okay, then we'll thank Vinita. So the next talk is by Saurav Kumar, who has finished his PhD from IIT Bombay, and he will be talking us through generalization of path following problem, a guidance perspective. Over to you, Saurav.
Thank you. Good afternoon, everyone. Today I will present the generalization of path following problem, guidance perspective. So this work I have done in my PhD, and this work was done in collaboration with Professor Sinha from University of Cincinnati. So let me first define what do we mean by path following problem. So consider you want to go from point A to point V, then what are the different ways one can go or a robot can move. So there are typically three approaches by which a robot can move from location 1 to location 2. The first one is waypoint navigation, in which we assign a sequence of waypoint to the robot which it has to follow in a sequential manner. In the trajectory tracking control problem, we give a temporal evolution of each space coordinates to the vehicle which it has to follow, while in the path following problem we relax the temporal constraint. Then why path following is important? So the path following problem relaxes the fundamental limitation associated with the trajectory tracking control problem, that it has a difficulty in making the L2 norm of the position error arbitrarily small, particularly in the presence of unstable zero dynamics. So what are the limitations for this path following existing path following strategy? So in the literature, most of the existing path following strategy were primarily developed for straight line or a circular path or any combination of these 2-3 paths. So then we came up with an idea that what is the thing which is restricting the path following strategy to generalize for any arbitrary path, and can we use the concept of missile guidance to generalize the path following guidance strategy? So the answer is yes. So instead of thinking path as a smooth curve, we thought path as a trajectory or a continuum of position of a virtual target, which the UAV has to follow. Now, if we can design a guidance strategy such that the UAV converges to the virtual target point and it remains there for all future time, then we can ensure that the UAV will follow the desired path. Oh, okay. Now, how can we ensure that the UAV will converge to the pseudo target? So there can be multiple ways. So initially we tried that if we nullify the relative separation between the UAV and the pseudo target, then we can ensure that the UAV will remain on the desired path. However, it turns out that we are unable to follow any arbitrary curvilinear path. It showed good performance when it has to follow a smooth path. So then we come up with an idea after several iterations that if the UAV follows a tail chased motion towards the virtual target, in order to follow it, then we can ensure that the UAV will follow any arbitrary path regardless of its fast curvature changes and all. So by nullifying the relative separation by following a tail change, we can always ensure that the moment the relative separation goes to 0, its derivative will be also 0. So as a matter of fact, that when the UAV converges to the pseudo target, it never leaves it, and thereafter it follows the desired path. And here we show the performance of the proposed approach when it has to follow a complex helical path, and one can see that the UAV follows the desired path by done. So UAV follows its desired path irrespective of fast curvature changes and all. Yeah, thank you. So these are the references which, if you are interested in maths, then you can read it.
My question is, like, you use a virtual point on the path and that is moving, you are tracking, then that becomes a trajectory tracking problem.
No, but here a speed assignment is independent. Here speed is a choice which you can assign.
Okay, you are
in trajectory tracking problem, when you parameterize a path in terms of a temporal evolution space coordinate, then your speed is also fixed.
So your guidance law will decide at which speed the virtual target also will.
Yeah, even a designer choice. It's a designer choice. You can assign the speed by which the UAV has to move on that path. We can assign that. Yeah. Yeah. So we have given those results in our paper. So when we take the speed as a time varying function, it also works.
Okay, then let us thank Saurav. Let us welcome Ajay. Ajay is a PhD student at ISC Bangalore, and today he will be talking on 3D reconstruction via camera lidar fusion for mobile robots, a Gaussian splatting approach. Over to you, Ajay.
Thank you, Surdeep, for the introduction. Very good afternoon, everyone. So, as first quickly introduce, like, what we are doing here is, like, there are already 3D reconstruction methods. So what exactly is Gaussian splatting? So let me quickly introduce this. So here, as you can see, that this is taken from the base paper of Gaussian splatting, where the ground truth is over here, and you can see the existing methods, how they have constructed from the ground truth. So this is coming out because of the neural radiance field based approach. Basically, like, let's say someone from over there will see in a certain way because of the lighting, but someone from over there will have a different reflection from my face and or the screen will have a different perspective about how that is looking. So let's say we cannot achieve this using simple voxel grid based of construction, right? So in a voxel grid, the properties will be like the location and also the RGB properties. But here we add one more properties that is called the radiance. So we include how much radiance the light is emitting in based on the direction of our observer, right? So just one quick overview about this is, like, we give some set of input of images, some captured from different orientations, and then we try to create 3D world. So that's majorly what Gaussian splatting is, and the previous approaches like NERF and all, they were unable to do this in quick real time. That is because Gaussian splatting based representation allows us this quick rendering. So now the problem is, now the challenge is not just we are taking some set of images. Now if we want to use mobile robots to capture this data, in the existing works, whenever we do this capturing, we have to make sure that the camera has to be moved very, very, very slowly, so that the difference, so that the map is coming to the scale. But and because of this, as you can see, the real scale is the LiDAR map that is towards the end. But in the existing state-of-the-art Gaussian splatting based approaches, you can see they're not coming to the scale and the trajectory is not exactly aligning with the real world. So this is one challenge when we use mobile robots into the picture. So what is the solution? So here is the solution we have proposed. Now basically we have a mobile robot with a LiDAR and a RGB camera. Initially, the architecture will take RGB camera, and then we will estimate the depth, and that will be sent to the sensor fusion module. And we know the relative transformation between the LiDAR and the camera, and we will be able to exactly identify where the LiDAR points are intersecting on the RGB camera. And using this data, we can infer the real world scale. And then we will send it to the rest of the Gaussian splatting to take care of the 3D reconstruction. So just one quick video, I mean, because of the interest of the time, I will give a highlight about what is happening. Here we have the depth map, and here we have the 2D map. And this is the RGB, I mean, the 3D reconstruction output. And yeah, this is how the final output will look like. And these are the some results where we were able to have lesser computational load and compared to the state of the art and etc. And these are the results where we were able to achieve less RMS error because of the scale compared to the real world scale. That is one. And now the future work will include AR/MR integration, where one of the work I would like to show, I mean, what is the use of using AR integration, MR integration, etc. So that's the overall context of this work. Thank you.
Questions?
So I have a question. How the background effect is in reconstruction process? How the background effect is in the reconstruction process?
Background of the image?
Yeah.
So we will have the same background taken from multiple perspectives. So in that way, we will not have the same set of light that is emitted from all the directions. So that even though the background is captured, I mean, if it is captured on only very few instances, we will have Gaussians that are extremely like unscaled compared to the real world. It is possible that you can see here some of these Gaussians whenever they are not properly aligned. When we have very few set of images in the beginning, which is not completely taken care of, then we will have the map output not in sync with the actual ground truth. So we have to take multiple orientations of the same background, then we will have much better output. Yeah.
Thank you.
Hi.
Yeah. Hi.
So is this real-time reconstruction?
Yes, this is real-time reconstruction.
So while actually doing the 3Ds, yes, you have the pipeline of having cold map and as well as the splats being reconstructed, no?
Right.
So what is the hardware that you are using on the board?
So the hardware that is used on the robot is only Raspberry Pi and the LiDAR, 2D LiDAR. We will transmit the images to an edge computer, which will process in real time for us.
And also, are you using this 3D map for relocalization, or do you know the pose already?
So the pose is coming from the LiDAR. So one of the challenges, like for even to capture the pose just through the images, it will be computationally expensive. So to avoid that, we are using LiDAR as a means to send the pose to the to the Gaussian splatting as well in the architecture.
So for the LiDAR localization, you should know the map, right? Do you know the map?
No. For we are creating the map, both the LiDAR and the 3D reconstruction at the same time. Yeah.
So you are running SLAM based on the LiDAR?
SLAM based on the LiDAR, yes. And the
then
3D reconstruction from the Gaussian splatting, yeah.
Okay.
Yeah.
Thank you.
Thank you.
Can you comment on the computational effort as compared to the other methods which you have shown in the beginning?
Right.
From your method?
Sure. So in the previous state-of-the-art work, they don't use any monocular depth estimation. We are using two models. One of them is unidepth and another one is depth anything. So you can see over here where using the unidepth with LiDAR, we were able to have about approximately 25% to 30% difference in the computational load compared to the state-of-the-art, that is mono-GS without LiDAR. Yeah.
You are not comparing with LUTs.
No, no, because there is already existing state-of-the-art work within Mono.js.
So can you go to that slide where you were talking about the pipeline, like? Yeah. So you have used in between some feature extraction, those methods also. Because I'm seeing that from your RGB camera, you have the monocular depth estimation. Those things are coming, right?
So there is no specific feature extraction, and because we already, I mean, feature extraction could be useful when we don't know the LiDAR. I mean, when we don't know the initial pose of at which the frames are taken. But in this context, we are completely using LiDAR to localize entire things. So there is no need of
like bundle adjustment. Those methods, those are not coming in picture.
No.
Okay.
Thank you, Ajay. Okay, the next talk we have is by Suprakash, who is a PhD student in ISC, and he will be talking on exploring multimodal input modalities for robot control. Over to you.
Thank you for the introductions. So basically, as a researcher, we always try to make the system autonomous so that the system can perform tasks for us by autonomously without needing any constant human input. But even with those highly autonomous systems, their human oversight is crucial for handling any unexpected situation that may lies beyond the system's capabilities. That is to ensure safety, accountability, and ethical decision making around the robot's surrounding space. So because of that, a researcher and designer are exploring on incorporating natural input modalities such as eye gaze, gesture, and speech to create an intuitive, efficient, and user-friendly interfaces for robot control. So in our work, we try to evaluate those input modalities in the context of a practical human-robot interactions. So basically here we are conducting 2 user studies. So first is a single task conditions where the object is to manipulate the manipulator by using these modalities. For eye gaze and gesture, here it is using a fixation time of 1.5 seconds. Where for eye gaze, wherever the user is fixing her eye on the screen, it detects as a click event, and based on that, the manipulator will move to that location. And for gesture, user have to orient his hand and fix his hand for around 1.5 seconds, and based on that, the manipulator will move to the location. So this is for single task condition, and for the dual task conditions, we have a mobile robot. So the object is to drive the mobile robot from one point to a pickup point, where the user will perform a pick and drop task, and that pick and drop task will be conducted by using those modalities. So this is the pick and drop task where user will pick up that orange object and drop it onto the platform of this mobile robot. So here the underlying work is same where you have seen in the single task condition. So I'll just skip the videos. Charlie. So these are the voice inputs. Hotel. So they have written videos. Coming to the result sections, what we have found is that the average task completion time is consistent across 2 tasks. But when you look at that the cognitive load side, you see the gesture has the highest cognitive load, while in dual task study, eye gaze has the highest cognitive load, and other modalities are in between both the tasks, which actually conclude that the effectiveness and suitability of a particular modality does not depend only on the user interface or user choices, but also on the task complexity and the context scenario. So this insightful is actually particularly important if you are trying to design an interactive systems that are intended to scale to a real world multitasking environment, which considering not just how fast the user can perform the task, but also how cognitive demanding the experience is, especially when they are doing multitasking involved. Yeah. So this was for me. So any questions? Yes.
So slide 5.
Yeah.
Yeah. So the question is that this figure that you are showing here, it is based on experiment for how many runs?
Yeah, so for the single task condition, so the objective here, I'll just show you one minute. So here in the single task video, if you see there are letters are coming, like okay, and these letters will change based on when the manipulator will move to the particular location. So in that they have these letters already assigned. So in the single task condition, so whichever letter is coming, the objective is to the user to move the manipulator to that location by using this model. So this we conducted for 10 times for each users, and for the dual tasks. So for the dual task, we are measuring how much time the user is taking to make the mobile robot go to the pickup point, pick the orange object, drop it onto the platform, and then again taking it to the other point. So for these are the measurements. So task completion time we are measuring, and the cognitive load we are measuring by a NASA TLX score. It's a.
My question is simple. For how many runs the figure must be based on, say 100 runs or 50 runs or 20 runs. For how many runs you have?
So we conducted user study using 10 participants. So we give them a trial run so that they get accommodated with how to utilize those modalities. So it depends on the users how much time they are taking to get accommodated.
10 participants, and
so
for each of them multiple runs.
Yes. Okay.
Let us thank Suprakash. So the next talk is by Bazila, who is a PhD student at IISc Bangalore, and she will be talking on event-triggered control for resource-constrained systems. Over to you.
Good afternoon. I am Bazila. I will be presenting on event-triggered control for resource-constrained platforms. We know robotic systems are resource constrained, and this constraint gets amplified when we have small robots. But when we look at nature, we see small flying insects and birds. They are able to navigate through cluttered environment with much ease, and that too by just relying on visual cues. So we can get inspiration from nature and try to add them to our control architectures. In addition to that, we see that how a biological neuron works is it doesn't react to every stimulus which is given to it. Rather it only reacts when the stimulus goes beyond a certain threshold. So this inspires our work, which is based on event-triggered control. It has been seen that flying insects like honeybees, they rely on optic flow. That is a apparent motion of objects in the visual scene. So honeybees and optic flow is numerically given by the ratio of relative velocity to the relative depth. And it has been seen that honeybees and these insects use a constant optic flow for landing. This allows them to have a smooth touchdown with the ground. In our approach, we also rely on the same fact. We have a downward facing monocular camera from which we extract the optic flow. Here you can see the optic flow dynamics is a non-linear equation. And in addition to that, near the ground effect comes into picture. And also, if you are landing on a dynamically moving platform whose motion we don't know, it creates uncertainties in our system and leads to difficulties while landing near the ground. So we come up with a data-driven approach where we collect input and output data and come up with a linear model of the system using Koopman operator theory. So in our system, we collect data of optic flow and the corresponding accelerations. Once we have the linear model of the system, we use model predictive control to track a reference optic flow so as to achieve a soft touchdown with the ground. In our approach, we use a separate event triggering scheme for adaptation as well as control. In addition to having an offline model from the collected data set, we refine our model as we are going on in the mission. And we adapt our model as well as the control input based on the events which are based on the control YAPNA functions. Only when those are breached, we update our system. So here are the results where we have shown that we are able to get comparable results for landing when we use event triggered scheme, and these results are comparable to that when we have a time triggered scheme, but we are able to get these results with reduction in events by 58%. So this shows that continuous updates aren't necessary. We need to update only when it's required. So this paves a way for insect level efficiency, where we are not updating our hardware, but rather we are thinking like nature. Thank you.
So the formula you had shown for the soft landing problem, there were a set of 3 formulas. Those parameters, this one, right. So the parameters associated with them, will those be different for different landing scenarios? Or there is some scheme for fixing the values?
In this equation, x is the optic flow, which will depend on how fast or how slowly we are going. And u is the control input we are giving, and h is the height above the ground. In our approach...
That's fine. The exponential term, whatever is in the subscript, those are physical quantities or those are coefficients?
No, those are physical quantities. H of 0 is the initial height, and x reference is the reference optic flow we want to track. It can be a particular constant. For landing applications, we have a negative optic flow, so as our height goes to 0. In landing applications, we want to track a negative reference optic flow.
Okay, thanks.
In the simulations, we saw altitude getting negative. How is that explained? Like
which one?
The altitude, the third figure.
Here you can see it is the green one shows the motion of the platform, and the orange one is the time triggered scheme, and the blue one is when we are using an event triggered scheme.
So that's the global. That's because of the global coordinate itself, because it's getting negative. Fine.
Okay, let us thank Basila. Okay, so the final talk of this session will be by Meenakshi, who will talk on the Rome story, why quality data sets are the unsung heroes. Over to you, Meenakshi. Okay, by the way, Meenakshi has finished her PhD from ISC Bangalore.
Okay, Rome is actually a data set that we created during my PhD with Professor Ghose. And rather than going into the technical details of it, I thought that I will tell you why it is so important. Like nowadays you hear everybody is talking about AI, and if you really want to build smart systems, autonomous systems, why your data set matters a lot, and why we actually took this upon ourselves that okay, we will create this data set, and why it might also inspire you to do the same. So the picture you see here is it's a very inspiring thing for me, because every time we think about laws of gravity, we always have the gravitational constant. But if you actually read the history, when Newton proposed his laws of gravity, there was no gravitational constant. He just wrote it in terms of proportionalities. So the capital G came after a long time. There were a lot of experimentation, and people actually approximated capital G from those experimentation. So what we are doing is, when we talk about all this AI and all these data sciences, for us, we control system engineers, what it means is we have this ample amount of data and you're building models, you're finding the hyperparameters. And that's what I think one of the evening Professor Ghose actually told me, that was one of the discussions, that you basically are finding from your observation, you're finding a model. But let's now go to the inspiration for my thesis. I actually wanted to train, make my robots move like the way humans do. So in the order to do that, there was a lot of things like we thought that we will make it how do you move? You predict the environment and that you move. And then we thought, okay, so we'll do video prediction, but then we went to do video prediction, we found that there are no data set that actually condition on how the robot is moving. So I told Professor Ghose that, okay, sir, I have a hypothesis that if we add on the robot's motion, I think we will generate better predictions. And but we don't have a data set like that. So why don't we build a data set and then we test my hypothesis. So there goes the origin story of ROAM, which is the robot autonomous motion data set. So thanks to the graceful participation of everybody from the department, thanks to the chairman of aerospace department. This data set we actually collected it's an in-house data set. We collected it here in our department, different indoor spaces. And as you can see, different students also participate. I used to send out emails, please come, we are collecting a data set. And everybody turned out, showed up. And now data set has like more than 3 lakh video action sequences. It is open source. You can download it. It's in a TF record format. You can train your neural networks on that. Yeah, this is just, I am not getting into the details of the technicality. You can read the paper or you can come and talk to me. We benchmarked it to show that, yes, to show that my hypothesis worked, and it actually got into doing a lot more work. We actually showed not just video actually gets better, you can also learn the robot's action, like on what principles it is taking the actions. Yeah, so to finish up, to motivate you right now, this is just a number. It's been about 10 months. The data set has been downloaded more than 500 times. But to quote somebody, so I had the fortune of going to CVPR and meet Professor Michael Black. Anybody who works on computer vision algorithms, they will know Michael Black. He's a very famous professor, and I was very frustrated. I told him I went on to do this data set and I created this data set. I don't know what I am doing, creating a data set takes a lot of effort. So he said, if you really want to learn any new theory in computer vision or in AI/ML, think about creating a data set. It will give you depth of understanding. So I leave you with that. If you have a problem, do consider your data set, because data set is the most important part. It's part of your experimentation, it's part of your reproducibility, all of that. So do consider that, and thank you. And thank you, Professor.
Just a quick question. What kind of policies are taken for the robot when you're preparing the data set? Like, are they manually teleoperated, or is there anything else?
No. So robot stands for robot autonomous motion, right? So it has this collision cone based approach. So we had a LiDAR. I did not put all the maths. So it's based on the LiDAR, and it automatically detects the obstacle. So if you come in front of the robot, it will stop, it will decelerate, and it will kind of try to evade you. So that is there. Yeah.
Okay, thank you.
Yeah, just continuing from that question, right? So the robot does not have in its understanding how a human also will try to avoid the robot.
No.
Okay.
So when we actually collected the data set, we just asked people to just move at your leisure space, move around, and it will automatically avoid. It is impossible to kind of control people to not to avoid them, but we said that you don't have to do anything. The robot, if it comes close to you, it will avoid. And interestingly, when we actually there is one paper, it's still under review. We observed that with this kind of data set, when we trained it, we just not only got a vision predictor, we also got something which is an agent or an actor, right? What we call in RL, and that was actually mimicking the behavior of that obstacle avoidance module. Okay. So it was actually predicting that if somebody is coming close, it was predicting that the action is like either decelerate or take a turn. Yeah.
Okay. Let us thank Meenakshi then. Okay. We come to the end of this session. We'll ask Professor Ghose to say a few words for the participant and distribute certificates to them.
Thank you. I think this session was very nice because I came to know about the work done in IIT Madras and IIT Bombay. Of course, I came to know the work that is done here as well, but I think these talks are nice for all the participants. You came to know what is happening here and other places. And the message that comes out here is that AI and ML is playing a very major role in many of these applications. So thank you very much. Very good pieces of work. And I wish all of you to submit your work. Some of you have already got your PhDs, but others who haven't, I wish you all the best that you will also get your PhDs very soon. Thank you. So
call them one by one. So first we have Vivek. Next we have Ishfaq. Shubham. Abhinay. Vinita. I think she is left. Meenakshi. Saurav. Ajay. Suprakash. And Bazila. Thank you, sir.